is to explain you what is a VSM. Of course, many of you know what is a VSM and why VSM are so great and you should all use them. That is the idea of this talk. So this is based on joint work that our group in Tel Aviv has been doing for several years, and here are listed the people who contributed to this research in the last 5 years, let's say. So these are the contributors from the last 5 years. You see, not all of them are from Tel Aviv. One is from the electricity company, one is from Torino, Fabio Maturile. Pietro Lorenzetti was in Tel Aviv, but he is now at the University of Nancy. Okay, so let's go to our business. So the traditional way in which power is generated in an electricity grid is from various kinds of thermal energy sources such as coal, nuclear reactions, other fuels, which are transformed into mechanical power. The mechanical power turns the axis of a generator. The generator rotates and produces electrical power. Okay. Now, this is now, it was for the last 120 or 130 years universally accepted that electricity grid is AC because there was a big dispute on this matter between Edison and who advocated for DC, and Tesla and Westinghouse who advocated for AC, and they were right. AC was the way to go because it's easy generation. You don't need contacts on the collector of the generator, easy transportation, and easy transformation. So maybe the most important, easy transformation, because DC, there was no way to transform DC 100 years ago, or until recently, there was no way. Now we have DC converters, but that's a relatively new thing. Okay, and not only that, DC synchronous generators have a wonderful property that if you connect them together in a grid, then they synchronize. So without any control, without any, that has been done 120 years ago, when they connected two generators together on a line, and they brought them to practically equal frequencies, and then they just connected them, and then they remain synchronized. From the moment they are connected, and if it doesn't blow up, because if you are connecting them in a wrong phase angle, then you get a huge current. But if you are careful and you connect them at the correct phase angle, then they remain synchronized. After that, you can do all kinds of perturbations on the system, like load changes and priming torque changes, and they remain synchronized. So that's a wonderful property of synchronous generators, which in fact has not been explained until 2012. This wonderful property that they do synchronize by themselves. This has been mathematically for the first time seriously looked at in a paper by Florian Dörfler and Francesco Bulo, which appeared in 2012. And I will talk about it later. Okay, so the external appearance of synchronous generator, you know, and here is a schematic representation of a synchronous generator, in which you have the three stator windings, and in the middle you have the rotor winding, which is rotating in this direction. And I also showed on the same axis as the rotor winding, I have shown also a damper winding, this red one, which is short-circuited and which acts as a damper, as a main here. Of course, this scheme, this representation is very much simplified. It doesn't really look like this. And in reality, you can have several poles for each phase, and you can have a complicated shape. But the basic idea is that you have the three stator windings connected in star. The center of the star is not connected, and then you have this rotor on which you have an electron. And okay, there are generators where you don't have the rotor winding, permanent magnet generators, but we don't discuss those because we only discuss generators which can be connected on a grid. Permanent magnet generators cannot be directly connected. So we don't discuss those. Yeah? And here is a simplified block diagram of this conventional synchronous generator that you have had on the previous slide. So this is a very much simplified block diagram of a conventional synchronous generator. Let's try to find our way here. So this is actually not only the synchronous generator, but it also includes, this picture also includes the excitation controller, the field excitation controller. So the controller which controls the current of the rotor is here in this green box. And you have the prime mover, and then you have the frequency loop mechanism, which is also part of the prime mover. So this upper part here is not the generator, it is a prime mover, together with the governor of the prime mover. And the actual generator is in the red frame. And in this red frame, you have the active torque, TL, which is an addition between the nominal mechanical torque from the prime mover and the group torque, also from the prime mover. So together they give this active torque, TL. And from this active torque, you have to subtract the electric torque, which is due to the currents flowing in the stator windings. And the difference will act on the rotor in the sense of the mechanical mass of the motor, in the sense of either accelerating or decelerating it. If this difference is positive, then it will accelerate the rotor. You see the transfer function. If there is no friction, then it would be just 1 over Js. So it would be you integrate the torque and you get the angular velocity, and J is the inertia constant of the rotor. But you have also this T because you have some friction also, some mechanical viscous friction in the generator. It's a very small term, but it exists there. And after this mechanical integration, which is called the swing equation, this part is the swing equation, you get the angular velocity of the rotor, which is omega. And this you have to integrate again to get the angle of the rotor, theta. And then, once you have the angle, and you have also the rotor field which comes from the excitation control, you have a certain rotor field, MIF, where M is an inductance term, and IF is the rotor current. So you put together the angle, the rotor field, and the frequency, omega, which comes from here. Yeah? And you put it into this formula, and you get what is called the synchronous internal voltage, E. Now, in this formula, you see this strange notation, sine with a tilde on top of it. It means this. So, a sine with a tilde on top of it just means a sine, and then a sine delayed by 120 degrees, and then a sine delayed by 240 degrees, or equivalently advanced by 120 degrees, as it is written here. So, this you get a synchronous internal voltage. Now you have this, you compare it with the grid voltage. The synchronous internal voltage is a voltage induced in the startup due to the movement of the rotor. And you compare it with the grid voltage, and this voltage difference falls on the stator impedance. So the stator impedance is Rg plus SRg. It's actually a bit more complicated because you have coupling effects between the three windings, but these coupling effects can be reduced to an equivalent Rg and Rg, so that this formula is actually correct as written. It includes the coupling effect. And then you get the stator currents. And the stator currents will produce by this very simple formula the Q component of the current times the magnetic field of the rotor will give you the electric torque of the machine. And that goes back to where we all have already been here. So we actually have covered everything. I have not explained the field current controller. Okay, the field current controller looks at the difference between the desired reactive power and the actual reactive power. And at the same time, it also looks at the difference between the desired point of common coupling voltage, so where the generator is connected, and the actual voltage, so the voltage difference, and we multiply this voltage difference by a so-called voltage droop constant, dq, and then these two terms are added together and integrated, and that gives me the rotor field. So if I increase this rotor field, which comes from here, then the synchronous internal voltage amplitude increases. Yeah, because it appears here in this plot. Yes? And okay, here in the frequency loop, what do you have? So the prime mover produces a nominal mechanical torque, and in addition it produces this loop torque from the governor, which looks at the difference between the nominal frequency of the machine and the actual frequency of the machine here. And this difference, you would like to just multiply it with a droop constant, which is dc. But you cannot, because it is a complex mechanism which does this droop. There are valves to be opened or closed, so it doesn't react immediately. It's actually a complicated system, which is represented here, very much simplified by a low-pass filter, 1 over tau x plus 1. So tau would be the time constant of the droop. And after this filtering through the time constant of the droop mechanism, you get a droop torque. Now I think I have really covered everything in this diagram. Yeah. Now let's see what is the main stabilizing mechanisms which are present in such a conventional synchronous generator. So it is the inertia, which does not allow the frequency to change quickly, because if I go back, the inertia, you see it here, this J. So it is a factor, it's 1 over J sits as a factor in this. You can neglect D, and you think of this as an integrator with a factor of 1 over J. So if the inertia is big, then you multiply this with a small factor, which means that a change in the torque balance, mechanical torque minus electrical torque, a change in this torque balance will not quickly change your frequency. Yes, the bigger the inertia, the less quickly will the frequency react to an imbalance of torques. And this has a stabilizing effect. We don't want the frequency to change quickly, because there are reasons for that. We will get back to it. And the other stabilizing effect that a synchronous generator, including the governor, has is a frequency droop that I have already explained earlier. The droop torque, which is which was this droop torque, which comes from here. Yeah, and now when inverters started to be used in the power system, then inverters had none of these stabilizing effects. They did not have inertia and they did not have a frequency droop. Then slowly these things started to get into inverters, and then people started to distinguish between grid-forming inverters and grid-following inverters, for the reason that if you replace I'm now talking not what is written on the slide. So if you start in a power grid to replace the synchronous generator with inverters, and you don't do it in a careful way, which means you do not take care for the stabilizing effects to be present in the inverters, then the grid loses these nice properties, the inertia, the frequency loop, it loses them gradually. And as a result, it becomes unstable. Now, to understand this mechanism of becoming unstable, you really have to analyze these nonlinear equations of the synchronous generator and the nonlinear system equations of huge number of variables that arise when you interconnect several synchronous generators. And as I said, this has not been seriously done until 10 years ago. So it's a very complex problem to understand it, but it can be shown that if the inertia tends to vanish, and if the group tends to vanish, then the system easily becomes unstable. And how do we notice that it becomes unstable? Not necessarily that it suddenly gets out of synchronism, but it is less tolerant to perturbations. So perturbations are, the main perturbations are short circuits on lines and generator faults. When a generator suddenly has some fault and it shuts down, then you lose generating power, and it's the same effect as a sudden increase in consumption. And these events can trigger oscillations which are planned. If your system is stable, they are there, but as you lose inertia and you lose loop, they are less and less dense. And at some stage, you really reach the situation where they are not dense at all, and the system becomes unstable. Okay, let's see this picture is, it shouldn't look like this. It has been distorted. I don't know what happened here. Okay, this is not the real picture. It has been something happened in the process. When I was in my room, it was still okay. So the idea is that if you have a fault of a generator or a sudden increase of consumption, which is less likely, but it would be the same effect, then the frequency, this axis is meant to be the frequency, then the frequency of the grid goes down, it reaches the so-called nadir, and then it goes back, it has some damped oscillations, it goes back to a level which is lower than the initial level, and then later, due to an effect which is called secondary control, which I have not discussed, but you know what it is, it will eventually go back to the original frequency of the decay. And the slope of this decay, the slope of the decay here, of the initial decay, is the inertia in the system, or is dictated by the inertia of the system. And then after a while, the droop kicks in, the frequency droop kicks in and gives extra power into the system, and this brings back the system to a new equilibrium which is lower, at a lower frequency than the old equilibrium, because it's a new equilibrium point corresponding to a new situation. And then the secondary control kicks in later and sees that, okay, we are now at a different equilibrium point, so we have to change the power from the generator, and it will go back to 50 Hertz. Now, this is a typical scenario that all electricity companies look at, and they want to make this nadir, the lowest, which is very distorted in the picture, they want it to make it as high as possible. So the minimum point to be as high as possible, and this slope to be as small as possible in absolute value, because it's negative. So you want to minimize the absolute value. And why? Because there are all kinds of protection mechanisms in the grid which look either at this kilo, that's the local rate of change of frequency, or at the frequency itself. So they look at the appearance at a certain moment. And they disconnect, so they start with load shedding. To save the system, they start disconnecting loads, and then if the frequency goes down too much, then the generators start disconnecting because they want to protect themselves. And we want to avoid this from happening, and for this reason we need a large inertia to prevent the big slope here, and we also want to prevent the stability to be too low because that would cause the generators to disconnect. So the danger is that this penetration of inverters which are not good players, this system will become more vulnerable. So the robustness of the system will become vulnerable. Let's see what is the difference between a synchronous generator and a power electronic converter. So I already told you inertial behavior. Okay, that I told you. Now, large short circuit current. If there is a short circuit, which is one important alpha fault, then a synchronous generator can give huge overcurrents, many times more than its nominal current, because nothing happens. If you do it for a short time, nothing will happen to it. Only if you give it for hours, then it could overheat and could get destroyed. But for a few seconds, it's not a problem. It could overcurrent in a synchronous generator. In an electronic converter, that's not the case. You can allow 20% overcurrent, 30% overcurrent, something like that. Then a synchronous generator automatically does filtering of the harmonics for you because it has a low output impedance, and so the higher harmonics are sort of short circuited by the generator, so they are diminished. And that is not the case for power electronic converters. And most power electronic converters also have no inertia. Okay. How can we help the electricity grid to transition smoothly from the situation in which it is dominated by synchronous generator to the situation in which it will be dominated, in which the production will be dominated by switched power converter. So the idea that my group is trying to push is that instead of completely reinventing the power grid according to new principles, we want to keep it the same. And this is also much easier for the power system operators because they can continue to work in the usual way. And the idea is that we include the equations of the synchronous generator into the control of the conventional inverter. And in this way, we can preserve all the good properties of synchronous generators, and not only that, we can actually get better properties than synchronous generators. In many respects, we can obtain much better behavior than synchronous generators. Let me just give you one example for that. Well, again, my terrible picture, which you cannot read, but this goes down to a nadir and then it goes back. If your group would act instantly, which in a real generator doesn't happen because it has some mechanics attached to it, so it cannot react instantly. But if it could react instantly, then you would not get this nadir at all. It would go down from the higher equilibrium frequency, which presumably starts from 50 Hz, and then it would go down to the new equilibrium frequency without going to a minimum. Yes, it will just go down in a monotone way to the new equilibrium frequency. If the loop could act immediately. And in a power converter, if you imitate the behavior of a synchronous generator, but you make the loop to act instantly, which you can do in a power converter, then you get that. So the nadir disappears. Now, where can virtual synchronous machines be used? So you have here, it's especially in solar and wind farms and in storage systems, but you can also use them on the consumer side. You can attach them to car batteries and chargers of car batteries and to various other large consumers, because then these consumers will also behave like synchronous motors. Yes? And that they have the same good properties like inertia and loop, they can also do. How to actually do it? So you here in this picture, it's an illustration. It's a very simple two-level inverter, but of course you can do it. I mean, in our lab we do it usually in three-level inverters, and Florian recently did it on a modular multi-level inverter in Kiel. In this example, it's a two-level inverter. It has a conventional LCL filter at its output, so everything is as usual. But so we have the drivers for the switches, and we have the PWM generator, and the VSM is actually only a change of algorithm, that gives the reference values to the PWM generator. So what we are proposing is only a software modification in the control algorithm of the inverters, which is now, I'm lying to you, it's not true, because you actually need either a much bigger capacitor on the DC bus, because if you want to provide inertia, then you have to provide this energy reserve that is needed if there is a drop of frequency on the grid. You have to give a big pulse of energy, and you have to have somewhere to take it. If you have only solar, an array of panels behind as an energy source, and you are using them using MPPT as a maximum power, and then suddenly you have to give more, you don't have. But so for this reason, to be able to give the pulses of the inertia, you need either a big capacitor here, seriously more capacitor than you normally use, or you need to have a battery. Preferably you should have a battery. So that's a hardware modification. It's preferable to have this kind of inverter always next to a storage, next to an energy storage. Okay. When you think of the first step of how to realize this, then you say, okay, I have the differential equation of a synchronous machine. I can run a simulation of them. And then what should I do? Should I create a voltage source which creates exactly the same voltage that a synchronous machine would provide? And then this voltage, I put it on the filter of my inverter, which is this. This is the filter of my inverter. Yeah? Or alternatively, I can compute what would be the current provided by my virtual synchronous machine, and I would run some current control loops to create exactly that current to go out to the usual filters of my inverter. When it turns out, so when we started to do this 11 years ago, or even more, 12 years ago, then we did it this way. We proposed, it was with colleague of mine, Kinshak Zong, at Imperial College. No, I was already not at Imperial College. No, he moved. He moved, and I moved. So anyway, At that time, we proposed it this way, so as a voltage source converter, and this turned out to be so it worked, but it was not working well. It doesn't work well. Why? Because if you have the impedance of your output filter in a usual inverter is very small. If you express it in per unit, it would be something like 0.05. That's the order of magnitude of the impedance of the output filter. By contrast, the output impedance of a synchronous generator would be of the order of 1.5 per unit. That's a huge difference. But, okay, so there are two reasons. One reason is this small impedance, you have to create for here a voltage so that it should roughly follow the grid voltage. Yes, not exactly, of course, but roughly it has to follow it so that you get a certain power. There has to be a certain difference, a relatively small voltage difference between E, the synchronous internal voltage, and the grid voltage, because the impedance is small. So small voltage divided by small impedance will give you the current that you want. But if there is any tiny measurement error in your measurement of the voltage, which obviously there will be something like 4 volts. That's the order of magnitude of the expected voltage measurement error, about 4 volts. Yes? Then when you think about it, this error of 4 volts, this will appear as an error in the voltage between this point and this point. And this error voltage divided by the tiny impedance of the output filter of an inverter will give you, for a 10 kilowatt inverter, it will give you something like 6 amps error current. That's impossible. You cannot handle it. And of course, that's scaled to any other power thing with scale. So one possibility to handle this would be to hugely increase the filter inductor of the inverter. That's not practical because the inductors are very expensive and very viable. So that leaves us then the second possibility. That's one reason. I told you there are two reasons. The second reason is purely mathematical. You can look at the equations of a synchronous generator connected to an infinite path, which is the grid, when you regard only one generator against an infinite path. And you get a system of order 5, nonlinear equations with 5 state variables. That's a simplified model, but it is a basic model. And you can ask yourself, is it stable? Yes, it's a mathematical question. Of course, it depends on the parameters. So when you choose correctly the parameters, then it is stable. Otherwise, it won't work. But real generators, as I said, have an output impedance approximately 1.5. If you try to make it work for output impedance per unit 0.05, it's not stable. It's not that you forget measurement errors. Suppose you have no measurement errors. You have everything that works perfectly, but the system is not stable because the equations are not stable. So, so there are two reasons why we must go with a second option, the current source, VSM. And
what do you mean by equations are not stable? What do you mean?
You have a system of 5 nonlinear equations which represent your generator connected to an infinite path.
Right.
And this, ideally, what you would like, when you express it in equal coordinates, you would like it to converge to an equilibrium.
Okay.
Right? And it doesn't. There is a region, a domain of in the parameter space. You have about 5 significant parameters. So you have a 5-dimensional space of parameters in which you have a region which is a region of stability.
So
You have to be in this region.
So you don't have even steady state equilibrium.
No. Or you might have, depends on the other parameters. You might have a steady state equilibrium, but with an extremely narrow region of the tension, so that a tiny change will make it unstable. This is also a possibility. So, by contrast, if the parameters are correctly chosen for this fifth order system, then the system becomes almost globally asymptotically stable. Now, this is a mathematical concept. It means that no matter from what initial state we start, no. There is a set of initial states from which it will converge to equilibrium. And the complement of this set has measure zero, which means that practically you will never be there. So it's an almost sure stability. Yes, it's not stability from any initial state, but it is almost sure. So the set of initial states from which it will not converge to equilibrium has measure zero. I don't know if that there is maybe to some of you it doesn't turn out, but okay. So if you are in a good choice of parameters, then you have this very strong kind of stability, almost globally asymptotically. For the grid connected general, yes, for an infinite bus, one generator on an infinite. Now, so let's discuss a bit this version with current control. So how do we actually do it? We have the synchronous internal voltage generated by our model of the synchronous generator. We have the measured grid voltage. We take the difference, and this difference, we don't put it on the real filtering output. No, we do it in the processor of the controller. We put it into this, so we divide it by the impedance Rs plus SLS, which is a virtual impedance. So we compute the virtual currents in the processor, in the algorithm, and in this way we obtain the current that we want, but this impedance we make it big, like it would be in a synchronous generator. So this is a big impedance. We get the correct currents that we would want, and this current is now the reference current for the current loop control. Current control loop. How does the inertial response look like? So it's a frequency. Let's just imagine that the grid frequency goes up, down like this. Of course, that never happens, but just in a hypothetical scenario to understand what this is doing. So let's say that the grid frequency goes up, down, like this. Then the power generated by such a VSM would be when the frequency goes down, it would be a higher level than when the frequency goes up. Yes? This is because you have an additional power injected, which is proportional to the derivative of the frequency. That is precisely what the inertia is. An additional power proportional to the derivative of the grid frequency. So it's not exactly a rectangle, you see, because there are other effects in the equations, but it is roughly a rectangular signal that follows this. And in a more realistic scenario, when you have a dip of frequency like this on the grid, then the power would behave according to such a graph. So you see that during the fast decay of the frequency, you have a big pulse of power. Yes, which is precisely the inertial response of your inverter. Now, I told you that in a VSM, you can make a VSM much better than the actual generator. And one aspect in which you can make it better is you can make the droop respond fast. And you can even make it not only a proportional droop which responds instantly, but you can make it even better than that. You can make the droop constant You can decompose the frequency error signal into a high pass component and a low pass component. The sum of these two would be 1. And then you multiply them with different loop constants. The high pass and the low pass, you can multiply them with different constants. The high frequency part, we multiply it with a higher constant because that gives you stability, the damping. And the low frequency component, you multiply it with a lower constant because you don't want to demand too much power from your power source because you have a limit on how much power you can give in steady state. I think that I am out of state and out of time. This is the same idea that I just told you. This is about over voltage right through, over and under voltage right through, which can be programmed very easily into such a DSM. This is reactive power control can be programmed to work with a bandwidth because some grid codes demand to have a certain deadband in the middle. I don't know why, but they demand it. Let's skip this. Skip this. An important damper windings. Okay, we can also do damper windings. We can in this algorithm we can include another few lines, and then we have as if we also have the damper winding of the synchronous machine. I skip the details of that. So this is still there. Simplified damper. Okay. Then here are various types of virtual synchronous machines which have been proposed in the literature over the years. So there is the one that me and Consortium proposed was a Synchronous. There is the Osaka model. There is Wisma, which has been proposed by some people in Germany. The self-synchronized synchrometer, okay, that was. Then we have other Wisma, other Wissing. You have the Kawasaki Heavy Industries, the VSM. You have the Syntef VSM. So there is like a zoo of various types of VSM that exist. And of course, I will tell you that ours is the best. And we have constructed actually in our lab in Tel Aviv, we have several VSMs which are synchronous, and we tested them in a lot of conditions so that to make everything very short because of the time, and they perform in a very robust and very stable way. This is now the simplified block diagram of a synchrometer, which is a type of VSM that we propose. So you see the red block is almost the same as the red blocks that we had for the block diagram of the synchronous machine. There is a small difference here in the impedance, in the state of impedance. You see, RG plus SLG is exactly like that they are in the synchronous machine, but then you have also a series capacitor. Why do you need a series capacitor in the stator impedance? Of course, in a real stator, you don't have a series capacitor. So this is to prevent DC currents. This capacitor will stop any DC current that might, by mistake, flow through your stator winding. Why? Because here we are dealing with measurements. You don't have real voltages. You have measurements, and you have PWM signals which all have a little tiny errors and biases. And these tiny errors and biases might create a tiny bias of a tiny constant bias of your output voltages. And because the output impedance at frequency 0 is very low, because the inductor has 0 impedance at 0 frequency, a tiny error in your output voltage could create a huge DC current. This is actually something that we encounter. And to prevent that, you put also a series capacitor. But the series capacitor, you choose it huge, so that at the frequency of 50 Hertz, it's negligible. It is like, it does nothing. at 50 Hertz, or at 100 Hertz, or at 150 Hertz, it doesn't. Yes? But it is there to prevent in steady state a DC current. Another difference is that you have a low-pass filter on the top to prevent some noises, and you have a saturation block on the integrator that gives you the angular velocity, because you want to prevent your angular velocity to reach 100 Hertz or 30 Hertz. You give it certain limits that you don't allow it to get out of those limits. Otherwise, this red block is exactly like a synchronous machine. Now, you have here the virtual currents. The virtual currents, you put them into a current limitation. And this is very nice because here you have a DQ component. You transform them into DQ components, and you limit the DQ components. And by limiting the DQ components, it means that after you actually generate these currents, you have here the reference current, which is after limitation, yeah? And you have the current loops, which I didn't mention how to do them, but the idea is that the actual currents which you get will remain purely sinusoidal, so your limitation will not distort the current. You limit the DQ components, but the actual ABC currents remain pure sinus. I think that I have exceeded my time, so I have many more slides, but I can give you the slides if you want. But I tell you now I don't do any more slides, I just tell you that there are various games that you can play with virtual synchronous machines connected in a grid. And one important such game, which Florian that was his main topic in his thesis, was virtual friction. So virtual friction means that you want to prevent the generators from oscillating against each other, the inter-area oscillators. Now, in a real system, there are all kinds of ways to do that, power system stabilizers that you put on the excitation control and so on. In virtual synchronous machines, or in a grid in which a part of the machines are virtual synchronous machines, you don't have, not all. Some could be conventional generators, and some yes. Here you have a wonderful new possibility to do the damping. Namely, you pretend that the axis of the different generators actually touch each other through a clutch. So there is friction. So as if, let's say, one hand represents one generator axis and the other is the other axis, and they rub against each other. So that means if they want to oscillate against each other, then this oscillation will dissipate energy, so it will the oscillation. Yes, and you can introduce this virtual friction between generators in a grid, and it has a very nice effect of killing the inter-area oscillation between generators. And what you need to be able to do this is communication lines between the generators. Namely, you need communication lines from each generator to some central controller, which receives the omega from each generator, and then computes an weighted average of all these omegas, which is called the center of inertia frequency. So you have an omega center of inertia, which is an average frequency, and then you send this information back to all the DSMs, and each one pretends to be to do friction against this average frequency. So if it's faster than this average frequency, then you add a torque to the swing equation, which slows it down, and the other way around. If it's too slow, then you help it to speed up. And it turns out miraculously that this scheme can be made quite immune to delays in the communication. So basically, for up to round trip delays of 500 milliseconds, which is a lot, this scheme works. Why? Because omega doesn't change so fast. The omega is changing at a slow rate. So if you have this round trip delay, as I said, and you can align the signals, as Florian explained, using timestamps. You can align the signal, then you can actually help to diminish the interrelay oscillation.
Okay.
Sorry, George, can you show your slides one by one? Because it is recorded, so the...
I should carry on and show them.
Yeah.
So this is a more detailed scheme of the synchronous, more detailed than the one on the previous slide. Okay, text. Network, okay. How to understand the electrical friction, you need a certain model, a certain reduced model of the power system, which is called network reduced power system model. Okay. Okay, a lot of...
Maybe we will have...
Okay. Okay, sorry, I jumped. This is a swing equation. This is the basic ingredient of the network reduced power system model. Here, this is it. This is an NRPS model. It's exactly you have not one. Why is it going without me? Because
Sorry.
okay, so this is a famous NRPS model. You have, this is not one equation, this is a system of as many, so for each generator you have one such equation, and here you have the coupling between the generators, because these are angles of the different generators, and they are here, the differences appear here. So a system of, I don't know, 50 such equations represents the model for the network of 50 generators. And then this is a manageable system in the sense that by working very hard you can get stability results for this type of system, for this type of representation of a grid, which is a very much simplified representation of a grid. Okay. Then here are many slides about how to obtain those matrices. I skipped, of course. I just, what happened here? I think, I don't know. Okay.
I think we can stop here.
I think we just show the slides.
Yeah, but
until the end.
Yeah, but it's
Okay.
So the future online audience can see the slides.
Yeah, but then
Okay.
we are clipping very fast, so they will not be able to follow.
You
Yeah,
do it.
I will do it. There are 100 slides.
Can upload the PPT.
I mean, YouTube will not do this.
Okay.
This is for here, mainly Florian's work.
Yeah, but then if you do this in YouTube also, there has to be some time between the two slides.
These are the region of attraction of the equilibrium point.
They can stop.
So here we do regions of attraction, and we show that as you increase virtual friction, the region of attraction of the stable equilibrium grows.
So I have, okay, while they are doing this,
Yes.
I have a question.
Yeah.
So you, is this BSM model built in practice?
Yes. We have 4 in our lab.
No, that's the lab, but industry.
So a startup company in Israel built with professional model,
Okay.
and we took it to Japan. There is a standard institute in Japan, and in Koreama, it's where they do very rigorous testing of inverters. They have it's called AIST. And we passed very nicely all the tests. So it confirms to IEEE tests, and it confirms also to sort of emerging IEEE tests, which are not yet formalized for grid-forming inverters.
I have 2 main questions. The first one is that have you ever considered about the stabilization dynamics in the